Okay, in this video I'm going to talk about Dalton's law of partial pressure, and then I'm going to talk about measuring the volume of a gas using downward displacement and what vapor pressure is. So because pressure is force per unit area, and because forces can be added to come up with a total force, if two gases, A and B, are exerting pressure, they're going to exert that pressure on the same area. So the total pressure exerted by multiple gases in the same container can be added just by adding the imaginary force that each gas is pushing with. So if I have gas A at pressure A and gas B at pressure B in a container, then the total pressure acting on the sides of that container is the total of A and B. Again, the area is the same, so if I can add the forces, I can add the pressures. That's Dalton's law of partial pressure. So really simply, if we have, say, oxygen and nitrogen gas in a container, and we're going to say that nitrogen is accounting for 65 kilopascals of the total pressure, which happens to be 100 kilopascals, we can determine what the pressure of the oxygen gas must be. So the pressure total is simply the sum of the oxygen gas pressure and the nitrogen gas pressure. So 100 kilopascals is the sum of the oxygen and the 65 kilopascals from the nitrogen. And so 35 kilopascals of that pressure must be coming from the oxygen gas. One time that this matters is when we consider doing downward displacement as the way to catch gas and record its volume. Imagine we have a beaker here. In the beaker, we're all full of liquid, and in the liquid is going to be some HCl. And then we take a graduated cylinder and we fill it up with water, and then we invert it into the secondary beaker so that all that water is trapped inside the beaker. And then we take a chunk of magnesium, we throw it in the container. Just a second, I'll write Mg. And magnesium reacts with the hydrochloric acid to produce magnesium chloride, which are really just dissolved ions that stay in the solution, and hydrogen gas. This hydrogen gas is going to start to form bubbles, and these bubbles are going to collect at the top of the container. Over time, the liquid that is in the container will get forced down by the gas bubbles, and we'll be able to see the volume of the gas produced in that graduated cylinder that's flipped upside down. So by downward displacement of the water, because the gas displaces the water down as it occupies the space up here, we can see how much volume of a gas is produced in that reaction. One of the problems with this method is that as the gas bubbles through the water, water vapor is going to collect up in the top here. So this gas is actually going to be a combination of hydrogen gas and water vapor. So we might assume that since this is pushing this out of the way, that this is at air pressure, or 101 kilopascals, if we're assuming a normal average atmospheric pressure. But the problem is that 101 kilopascals doesn't actually apply to just the hydrogen gas. That's the total pressure of the two gases that are in that. So we have to account for the vapor pressure. Now the vapor pressures, for some reason on this chart, I've got one, thank you to that source, but they're in torr. So instead of saying 101, I would say 760 torr is an atmospheric pressure. So let's just say that we were doing this experiment at 23 degrees. It's a little warm in the room, but still comfortable room temperature. Then the pressure total, assuming it's normal atmospheric pressure, should be 760 torr. We might assume that that's the pressure associated with the hydrogen gas, but we'd be forgetting about the water vapor pressure that would be created. So what we have to do here is we also have to account for the vapor pressure at that temperature. So we're going to say that that total pressure is made up of the hydrogen gas that we're trying to measure plus the water vapor. So 760 torr is equal to whatever the pressure from the hydrogen gas, that's the one that we actually want to know for the measurement we're making, and this 21.1 torr. So I can come up with the pressure of my hydrogen gas by subtracting away the part of it that's vapor, and I can get 738.9 torr, and that's how much of this gas volume pressure is resulting from the actual hydrogen gas that we're producing in the experiment. It's not a huge change, but it's substantial, 5% or something like that. So it's something that we can take into account in an application of how we use Dalton's law of partial pressure to figure out the pressure of a gas that we're interested in.